Peter Onufryk is a fellow and NVMe Technical Workgroup Chair at Intel. He has been very active in NVMe standardization and is the current NVMe Technical Workgroup Chair. He holds over 40 patents, has written several published articles and books. Peter earned a PhD to electrical and computer engineering from Rutgers University and an MSW from Purdue University. Please welcome Peter Onufryk.
Thank you, Mark.
Can you switch this?
Yep. So as Mark said, my name is Peter Onufryk from Intel, and I'm going to give an NVMe State of the Union, which is basically an overview of what is NVMe and what's happening in NVMe. So let's get started by taking a look at the historic NVMe organization structure. So we have a board of directors. The board of directors consists of 13 elected companies. You can see them on the bottom. The board is responsible for stewardship of the technology and basically setting the direction of the organization. Next, we have the technical work group. This is where the work where most of you that think of NVMe actually takes place. This is the work group that developed the NVMe Base Specification and where NVMe over Fabrics work occurs. Next, we have the Management Interface Work Group. The Management Interface Work Group standardizes management of NVMe storage devices. We'll go into a little bit about what that means a little later. Next, we have the Marketing Work Group, which handles outbound communications, press releases, our website, and so forth. And then finally, we have the Interop Work Group. The Interop Work Group works with UNH IOL to help create our Interop and Compliance program. So that's an overview of the historic NVMe structure. A lot of you are here and you're thinking of NVMe as kind of this new or relatively new technology. And the fact is that NVMe has been around for quite a while. In fact, 2019 is actually the 10-year anniversary of NVMe. So on this 10-year anniversary, let's take a quick tour of the history of NVMe. So back in 2009, we had PCIe SSDs. There was Fusion IO. Micron had an SSD. The problem with PCIe SSDs in that time frame was that you had to load a special PCIe driver with each SSD. So you couldn't just plug in the SSD and have it work like you'd expect with storage. So we got together and decided that we needed an interface specification to basically provide that you just plug it in and it works behavior. So the idea was we were going to take NVM HCI, which was an interface standard for client. We were going to add some enterprise extension to that, call that Enterprise NVM HCI, and then basically that would be the new PCIe interface standard. We started work in mid-2009. The first specification came out in March of 2011. It was called Enterprise NVM HCI 1.0, not NVMe 1.0. I put that there so I wouldn't confuse you guys. And Enterprise NVM HCI came out, and we quickly, as soon as it came out, we realized we made a mistake. Enterprise NVM HCI was not the kind of word that just kind of rolled off your tongue. The other mistake that we made is, we wanted an interface that was scalable from client to high-end enterprise. And the name Enterprise NVM HCI really didn't encompass that. When you hear that, you think of just enterprise applications. So we changed the name to NVM Express, which is NVMe, which is what we all know it by today. Shortly after, actually weeks after we released the 1.0 specification, a competing standards organization decided that they were going to standardize a PCIe SSD interface. And interface war began. Proponents of that competing interface standard basically were claiming that NVMe was controlled by a single company, it wasn't opened. So to address those concerns, we transitioned the organization from an industry work group to a promoter structure. So basically the promoter structure is like a board of directors using the 13 elected companies and basically the same mechanisms that we have today. After that, in 2012, in order to kind of continue our interface war work, we realized that we needed a marketing work group to provide a consistent message external to the organization. So we created a marketing work group. We realized in order to be a effective industry standard, we needed to have a compliance program. So we partnered with UNH IOL to create compliance and performance tests. We had our first Plugfest in 2013. At that point, we started seeing NVMe SSDs shipping, and we saw a number of OEMs deciding to standardize out-of-band management that they wanted for these SSDs. So we thought that the world would be a better place if we standardized out-of-band management, so we created the NVMe Management Interface Workgroup to standardize out-of-band management. In 2014, we incorporated as a nonprofit, and by 2014, the interface war was over. NVMe had won at that point. We started seeing volume shipments of NVMe. And NVMe was kind of a great technology for inside the box. It used PCIe. Now, PCIe can scale to some extent, but it doesn't really scale like people would expect for a SAN. So work on NVMe over Fabrics began in 2014. In 2015, we published the NVMe over Fabrics spec. Later that year, we also released the NVMe MI spec. In 2017, our compliance program was going really great, but we wanted to get more involvement from the technical community to basically determine, what features really needed to be tested in our compliance program and make sure that we got the appropriate industry input. So we created an interop work group. And then late last year, we ratified TCP as a transport for NVMe. So that's a brief history of NVMe. When you do an interface standard, one of three things, or when you do any kind of standard, one of three things can happen. The first thing is the standard can be stillborn. So you have a technical committee, they produce a spec, maybe some people make some prototypes, but it never really ships in any volume. So that's, I think we all know of specs where that's happened. Another thing that can happen is that the spec can get adopted, you can get some production shipments, but it only ships to kind of innovators and early adopters, and it never gets mainstream use. So it fails to cross the chasm into the mainstream, becomes a niche technology, and ultimately goes away. And then the third thing that can happen, which is the thing that we all want, is that it can become mainstream. And I'm happy to say that at this point, NVMe has crossed the chasm and become mainstream. So in the client world, high-performance SSDs and NVMe are largely synonymous. Market data shows that the NVMe and SATA crossover occurred last year. We continued to gain traction in the cloud, and we continued to gain share in the enterprise space. Looking at this data in a different way, we can look at the numbers. So in 2019, it's projected that we'll ship over 2 million enterprise drives, 17 million drives into the cloud, and over 100 million NVMe client drives. So I think NVMe has crossed the chasm and has become mainstream. I think the point at which I realized this was I was on vacation with my family in Washington, D.C. We were driving down the road, and there was a Supermicro billboard with NVMe all over it. And I realized that if I'm in Washington, D.C. and see NVMe on billboards, it's kind of become mainstream at that point. But NVMe is not only successful for PCIe SSDs, but it's now become the new language of storage. So we have 23 companies shipping 96 models of drives. We have 13 server companies shipping 93 models of servers. That's not surprising because NVMe SSDs are everywhere at this point. But NVMe is also gaining traction in a lot of other markets. So we have a number of companies shipping AFAs. We have a number of NVMe appliances. After NVMe over Fabrics was adopted, we had a huge number of companies supporting NVMe over Fabrics. We have 5 companies now shipping over 53 models of some form of NIC, RNIC, or HBA for NVMe over Fabrics. And we now have people building NVMe over Fabrics accelerators. You can think of these as kind of smart NIC companies. So with that brief overview of NVMe history and kind of the NVMe market, let's take a look at what NVMe has delivered this year. So this year, we released the NVMe Management Interface 1.1 specification in April. We released the NVMe 1.4 specification in June, and we're on track to deliver the NVMe over Fabrics 1.1 specification later this year. So where we're at is we've completed 45-day review. We've gotten some comments. None of them are technical. We need to integrate that and ratify it, but basically, NVMe over Fabrics should be ratified shortly. So basically, this year, we have 3 new specifications. If you take a look at the organization, we've never had 3 specifications come out in the same year, so that's a real accomplishment for the organization. We've continued with our PlugFests. So we had PlugFest 11 in June of this year. And in that PlugFest, we have an integrators list for NVMe. We also have a separate integrators list and compliance program for the management interface. So we're testing that. We have tests for NVMe over Fabric, and we also have tests for NVMe over TCP. Taking a look at the NVMe specification roadmap, we have 3 swim lanes, which represent the 3 specifications that we produce. At the top, we have the NVMe Base Specification. So this is the specification that defines the NVMe architecture, the NVMe command set, and the transport binding specification for PCIe. Below that, we have NVMe over Fabrics, which basically describes how do you scale the NVMe command set and the NVMe architecture over arbitrary fabrics. And below that, we have the NVMe Management Interface Specification. So historically, the Management Interface Specification defined how do you do out-of-band management. Now it encompasses more than that, and we'll see some of that a little bit later. So in 2019, we have the 3 specs that I showed you. You can see beyond that, we have NVMe 2.0. And NVMe 2.0 is going to be a major refactoring of our specifications, which I'll describe a little later. But before we get into NVMe 2.0, let's take a look at some of the details around the NVMe specifications. So in NVMe 1.4, we have 3 big new things. The first is NVM Sets and I/O determinism, which basically describes a way to get better QoS from NVMe storage devices. I'll go into what this actually looks like a little bit later. We have the persistent event log. You can think of the persistent event log as kind of a black box flight recorder for NVMe storage devices. Basically, you can record events in the persistent event log. Then if there's a failure, either an OEM or the original drive manufacturer can basically look at the persistent event log and see what happened. Now, a lot of you are probably thinking, well, this is really nothing new. We've had persistent event logs in SSDs forever. I think what's new here is that this is now standardized. So anybody can dump a standard log page. They can parse the persistent event log and see what's going on. Now, it's no longer vendor specific. And the third big thing in NVMe 1.4 is multipathing. Now, we've had multipathing in NVMe since NVMe 1.1. We added, multi-ported drives and multipathing. But what we've added is basically the ability to figure out how to select the best path. And I'll describe that a little bit later. For NVMe over Fabrics, we have 2 big new items. The first is an enhanced discovery system. So in NVMe 1.0, we had discovery, but it really wasn't scalable. We wanted a system that was more scalable to kind of thousands of nodes. So we've made those enhancements in an enhanced discovery mechanism. The other big new thing in NVMe over Fabrics 1.1 is the TCP transport binding specification. So this basically allows you to run NVMe over TCP, and I'll describe that a little bit later. NVMe MI has 3 new things as well. The first is enclosure management. I'll talk about that a little bit later. The second is the in-band mechanism. So recall NVMe MI initially specified out-of-band management. And what we found is a lot of things that we want to do out-of-band, we also want to be able to do in-band. We want to be able to download firmware. We want to be able to format namespaces. Those mechanisms existed through admin commands that are executed in-band. So rather than defining new out-of-band commands, we've had a way to basically issue those admin commands using the out-of-band mechanism. And then we built up additional capabilities in NVMe MI. And what people wanted is they want basically symmetry. They want to be able to get the same management capabilities in-band that they have out-of-band. So what the in-band mechanism does is it allows you to execute NVMe MI or issue NVMe MI commands in-band. And this is particularly useful for enclosure management. Finally, we made extensions to what an NVMe storage device is. I'll describe what that is and what the extensions are a little bit later. So let's turn our attention to I/O determinism. I/O determinism has 2 parts, NVM sets and predictable latency mode. So what an NVM set is it's basically a logical partition of the NVM associated with an NVMe storage device. And these are QoS isolated partitions. So an NVM subsystem may have 1 or more NVM sets. You can put 1 or more namespaces on an NVM set, and they're completely isolated from a QoS perspective. So in this picture, we have, you can think of this as an NVMe storage device. We have 3 NVM sets, A, B, and C. A has 3 namespaces, B has 2 namespaces, and C has 1. And basically, these are all on the same drive. And what NVM sets allow you to do is read or write to NVM set A without impacting the QoS associated with NVM set B. So that's the fundamental idea of NVM sets. The next thing that we added, or the next piece of I/O determinism, is predictable latency mode. So we can take an NVM set and we can turn on predictable latency mode for an NVM set. And what that does is it causes that set to basically oscillate between two states, the deterministic window and the non-deterministic window. The deterministic window is basically a state where you get great QoS. The non-deterministic window is a state where basically you do all your background operations and you actually execute any writes that were issued during the deterministic window. So basically, you can do reads during the deterministic window, and you get very good QoS. You can do some number of writes that get buffered, and then you transition to the non-deterministic window. Those are executed, and then you oscillate back and forth. So basically, you go between the deterministic window and the non-deterministic window. So this by itself isn't really that interesting, because when you need to do a read, you need to do a read. And the fact that you've got this deterministic window doesn't really help you. But what you can do in some environments, and this is primarily targeted towards cloud environments, is that you can take two SSDs, you can take a set on each, and you can put them both in predictable latency mode. So now they're oscillating between the deterministic window and the non-deterministic window. And you set them so they're out of phase. When you do writes, you write to both SSDs. When you do reads, you target that read at the SSD that's in the deterministic window. So now you have a way of getting great QoS. So I showed this example with two SSDs, but you can actually do it with one SSD because you can put multiple sets on it. So it works with sets on a single SSD. So as I mentioned earlier, NVMe is gaining adoption in a variety of different use cases. One of them is high-end storage systems. So here's a picture of a high-end storage system. Think of this as refrigerator-sized boxes that fill a room that are interconnected. As you'd expect, NVMe SSDs are a key part of those storage systems. But NVMe is also being used in the front end. So here we have an NVMe storage system, which is one of these room-filled arrays. We have multiple hosts. They connect to this storage array through NVMe over Fabrics. And what these hosts see are basically a single NVM subsystem. So in these sort of applications, you get some unique issues. So this picture shows a logical representation of the NVM subsystem associated with a storage array, or potentially with a storage array. Here we have three controllers. There's a host port associated with each controller. We have four namespaces, A, B, C, D. Namespace A is private. B, D, and C are shared namespaces. And basically, we have a media access boundary. So think of this as we have two refrigerators. They're interconnected, and the interconnection between those two refrigerators is the media access boundary. Now, what may happen in that and they all act as one NVM subsystem. You can have a host that has multiple ports into that NVM subsystem. So a host, for example, can use port X or port Z to access namespaces in that NVM subsystem. So let's say we're trying to get to namespace B. It may be the case that access through port X to namespace B may be higher performance than coming in through port Z because it's got to go through this media access boundary. So what asymmetric namespace access does, or ANA, is it's basically a mechanism to allow the NVM subsystem to communicate to the host, here are the different paths, and here are the good paths to use to access the NVMe, the namespaces. So it will tell you that port Z is the better path to use than the port Z. So it's kind of a multi-pathing enhancement. The other thing that can happen in these refrigerator-sized arrays that are interconnected is that this media access boundary may break. So it may be the case that you can't access namespace B through port Z. And ANA basically provides a way for the NVM subsystem to communicate that to the host as well. So that's NVMe. Let's turn our attention to NVMe over Fabrics. This slide shows a taxonomy of NVMe transports. So on the left, we have the memory transport, which is used by PCI Express. And then we have the message and memory transports, which are used by NVMe over Fabrics. So the message transport really uses a thing called capsules to transfer commands and completions. And and it uses messages. An example of the only example up until NVMe over Fabrics 1.1 of a message transport was Fiber Channel. The message and memory transport uses capsules for commands and completions, but uses memory semantics for transferring data. Examples of that are the RDMA transport, which works over InfiniBand, Rocky, iWarp, and so forth. So what's new in NVMe over Fabrics 1.1 is TCP. So the advantage of TCP versus these other transports is that you can basically run NVMe over TCP over any fabric that supports TCP. That means that you can use normal NICs. You don't need to buy special NICs. You can use normal switches. You don't need to buy any switches. So you might be thinking, well, that's interesting. I mean, we've run other storage protocols over TCP. That's nothing new. But actually, TCP is actually very interesting. So this slide shows performance of the NVMe over TCP implementation, the open source implementation, versus NVMe over RDMA using InfiniBand. Now, as with all performance data, your mileage may vary, but basically what this data shows is the red bar is the latency adder that InfiniBand adds, and the blue bar is the latency adder that TCP adds, and that's on top of what you would get to a direct attached SSD. So what you can see is TCP is about double that of InfiniBand or RDMA. RDMA adds about 10 microseconds. TCP adds about 20 microseconds. So it's double. That seems really bad. But when you put this into context, you think of, okay, a normal NVMe SSD has a read latency of, let's say, 80 microseconds. RDMA is adding 10. So you're basically comparing 10 microseconds for 90 microseconds for RDMA versus 100 microseconds for TCP. And so TCP allows you to disaggregate that storage without buying any special hardware, and the latency is actually quite good, and throughput's quite good as well. So as with any performance data, your mileage may vary, but it is an interesting technology. Moving on to NVMe MI. With the success of NVMe SSDs, people want to build NVMe JBOFs. So an NVMe JBOF is just basically a JBOD with flash that uses NVMe SSDs. A logical, or basically an architectural block diagram of what that is shown on the left. So we have an NVMe host, which connects to a PCIe switch, which connects to a bunch of NVMe SSDs. And then we have an instantiation of that on the right, which is basically the Facebook Lightning platform, which has an implementation very much like the one on the left. So one of the areas that you get into with enclosures is enclosure management. And the MI workgroup has standardized two forms of enclosure management. I worked at a company that builds SAS expanders, and my SAS expander buddies kept telling me that NVMe or PCIe would never succeed because it doesn't have enclosure management. And I always found that strange because I'd been shipping PCIe switches since day one, and we never provided any management software. For normal fan-out switches, I couldn't really figure out what the gap was. And what it turned out to be is basically indicators. So for very simple in-box expander applications, there's a need for indicators. The MI workgroup defined an extension to PCIe to do this. We brought that into the PCI SIG, and it was standardized. It's been around for a while now, and it's called Native PCIe Enclosure Management. It just allows you to control indicators with drive slots. And it's called MPEM. So that's fine for very basic enclosure management, but sometimes you really need real enclosure management. And that's what we've added to NVMe MI 1.1. If you take a look at NVMe and SCSI, the architectures are actually very different. But if you take a look at SCSI enclosure services, what an enclosure is for SCSI is very similar to what an enclosure is for NVMe. They contain a bunch of sheet metal, there's some power supplies, fans, temperature sensors, and so on, and you basically want to manage that. If you take a look inside of SES, you find out that there's actually very little SES or SCSI-specific stuff inside of SES. So what we've done in the Management Interface Workgroup is we've leveraged SES. We've provided a tunnel from NVMe MI to SES, allowing you to use SES for enclosure management to build NVMe JBODs. So that's enclosure management. A second addition to another big addition to NVMe MI 1.1 is an extension of NVMe storage devices. Now, in NVMe, we have this concept of an NVM subsystem. That's kind of a logical thing that we talk about in the NVMe Base Specification. But when you're providing management, you need to actually manage something, which is a physical thing. So we needed a definition for the physical thing that we were managing. And so we're managing NVMe storage devices. So an NVMe storage device is one NVM subsystem, one or more ports, and an optional through information device and an SM bus interface to get to that through information device. So there's two examples on this slide. So example on the left is just a straight PCIe add-in card with a single ported, one NVM subsystem. On the right, we have a dual ported drive, so dual PCIe ports. We have a VPD and out-of-band SM bus management interface. And this model served us well for a number of years. But basically, people are now building much more complex NVMe storage devices. So what we have is the device on the left, which is basically a carrier card. It has a PCIe switch. You can plug in two NVMe SSDs into it. We can't manage that because we can only handle one NVM subsystem. We don't understand what happens when there's a PCIe switch on an NVMe storage device. Another example that's common is on the right, which is a carrier card. Here we have a by16 card that bifurcates into 4x4s. It's got 4 M.2s. Again, we can't manage this because we don't understand what a carrier card is and how to deal with it. So what we've done in NVMe MI 1.1 is we've extended the definition and extended our management model. We can now manage multiple NVM subsystems. We can discover and manage PCIe switches. We can discover the SM bus topology and control muxes to talk to those NVM subsystems. And we understand connectors, and it can express the topology of the connectors. So we've adapted and can now handle much more complex NVMe storage devices. So that was an overview of kind of what's new in the specifications that were released this year. Now let's take a look at kind of the NVMe organization in general. And the NVMe organization has undergone, has going through 3 phases. In the first phase, it was all about a PCIe SSD interface, right? We wanted to have the same look and feel as what you have with a drive. You just plug it in and it works. So it was all about standardizing the PCIe interface, getting NVMe drivers written, getting them in box in all the major OSs. I'm happy to say that phase 1 is done at this point. PCIe and NVMe is largely synonymous, and there's an NVMe inbox driver in pretty much every major OS at this point. In phase 2, NVMe SSDs got adopted in box. We wanted to scale outside the box. So it was basically all about NVMe over Fabrics. And while work continues on NVMe over Fabrics, we're largely done with that. The underpinnings of NVMe over Fabrics are done. You can deploy NVMe over Fabrics. We will continue extending it forever, like we will with PCIe. But that work is largely behind us as well. So we're now entering the third phase of NVMe, which is kind of has 2 pillars to it. The first pillar is around standardizing mechanisms that are specific to NVM. So this is now using the unique properties of NVM and providing standard interfaces to that. So the I/O determinism mechanisms that I talked about earlier, that relies on NAND, are specifically targeted for NVM. Zone namespaces are another mechanism that are specifically targeted towards the unique properties of NAND. So that's the first pillar. The second pillar is entirely new use cases for NVMe. So as I mentioned, NVMe is gaining adoption in large storage arrays. That's been happening for a number of years. But NVMe is now getting interest from entirely new markets, such as automotive, which have very new requirements for NVMe. So we're now in the third phase of NVMe. The unique thing about the third phase of NVMe is that a lot of these initiatives are highly speculative. So if you remember, one of 3 things can happen to a standard, and only crossing the chasm in mainstream adoption is the good outcome. So it's clear that some of these initiatives may not succeed, may be stillborn, may become very niche. We need a way to manage this complexity. We don't want this specification to grow out of control and become hugely complex. So the way we're managing this complexity is we're repartitioning or refactoring the specification. So at the center, there'll be an NVMe Base Specification, which will describe the base architecture of NVMe used in all applications. Above that, we'll have command sets. So today, you're probably only aware of the NVM command set, but we're working on a key value command set and a zoned command set. We will probably continue to add application-specific command sets. So that's at the top. At the bottom, we're going to pull out the transport binding specifications into separate documents. So there'll be one for PCIe and so forth. So now we'll have a family of specifications, and if you're building a solution for targeting a particular market, you can basically pull out the specifications you need and ignore the other ones. And if we come up with a command set or a transport that doesn't gain traction, it will just fade away and nobody will see it because it'll be segmented in its own document. So one of the net results of this is we're going to take the 3 monolithic specs that we have and now refactor them into a pool of specs. So that's a spec restructuring, but that restructuring has also caused a restructuring of the organization. So this is the new structure of the NVMe organization. What I showed you earlier was the historic structure. So the new structure is we have a board of directors. The board of directors, still 13 companies. It is a steward of the technology, sets direction. Now we have 2 work groups. We have a marketing work group where we handle outbound marketing, and we have a technical work group. The technical work group will continue to be the place where the core NVMe technical work is done, but it'll also act as a plenary session to basically coordinate all the other work that's going on. And then we're moving to a task group structure. So a task group you can think of as a work group in the sense that a task group has a chair. It has a publicly published meeting time that's available on the NVMe calendar. The chair is responsible for sending out an agenda before the meeting. The chair is responsible for sending out meeting minutes. So it operates very much like a work group, but it's basically below below a work group. And we have 2 types of task groups. We have a topic task group, and we have a single technical proposal topic task group. Topic task group is basically intended for kind of long-running things. So things like the management interface, interop, ANA. We think that these things will continue pretty much indefinitely. We'll be adding new things or issues will be coming up and there'll be errata discussed. So we need a place for that to occur. So that's topic task group. The other type of task group is a single technical proposal task group. So basically here we'll spin up a task group. It'll work on a single technical proposal. When the technical proposal is done, that task group goes away. Now, it may be the case that some of the topic-specific task groups some of the technical proposal task groups turn into topic task groups, if they're widely adopted, but that basically, we'll see how that happens. So topic task groups are things like the key value command set, endurance group management, spec refactoring, zone namespaces. Topic task groups are management interface, interop, and ANA. Now, you guys may be looking at this and going, well, the management interface and interop previously were their own work group. Now they're a task group. Does that mean we're not we're removing emphasis on management interface, for example? And that's completely not the message that we're trying to send. What we're trying to say is we have a lot of technical activities going on in NVMe now. We have a lot of specs moving in parallel. We need a way to keep them all in sync, and the technical work group is the place that will keep them all in sync. And basically, this just basically allows us to parallelize the work. So NVMe has grown over the years. We started off as kind of a scrappy little organization defining a PCIe interface, and now it's the new language of storage. Much in the same way that companies transform as they go from a startup to a mid-sized company to a Fortune 500 company. You can't run a Fortune 500 company the way you run a 50-person startup. You can't run an organization like NVMe today like you did when we first started. So we've made a number of changes. First is we've moved to the task group structure, which will allow us to improve the throughput and keep everyone in sync. The second thing that we've done is we've created formal technical proposal phases. So basically, each technical proposal now goes through phases. We know what's done in each phase. We can track the phases. We have a document repository where you can look at, it's in the members only area, you can see where each TP is, what the status is, you can go through the revision of that TP. We've instituted a policy of creating an integrated draft specification prior to releasing any TP. What we found in NVMe 1.3, we had about 20 technical proposals. They all looked great on their own. We then wanted to release the spec. We tried to integrate them, and we found out that some codes were reused and some text didn't quite agree. So now what we do is before a technical proposal is ratified, we integrate it into the running draft spec, and we handle any of those sort of issues prior to ratification of the technical proposal. Finally, we were first started out, we had in-group voting, allows us to move very quickly, be very nimble. But now we deal with a lot of companies that are multinational, they have many sites, and we now move to electronic voting, which allows people to coordinate their votes prior to doing that. So in summary, NVMe has unified client, cloud, and enterprise storage around the common command set and interface. It truly is the new language of storage. The growth of NVMe adoption continues. You can see by the numbers, we've crossed the chasm. It's mainstream, and the growth continues to keep going. The NVMe organization has put in place a number of processes and initiatives to continue the rate of innovation, basically embrace all of the people that are trying to enhance NVMe, but do that in a way that compartmentalizes complexity and doesn't cause everything to be very complex if you're trying to build a very simple device. Finally, as NVMe enters its second decade, it remains true to its core principles of simplicity and efficiency. Thank you.